how am I doing for time? I've got about 10 minutes in which to show you how to add numbers that are as big as you like. How big would you like them to be?
Graham's number.
Yeah, that's too big. Not because we can't add it, but just because we can't fit it on a piece of paper. Let's have a pair of 3-bit numbers. Because that will fit. So we've got 2 3-bit numbers coming in. And I'm actually going to throw another bit, which is called the carry in. Right. So if these are 3-bit numbers, what are the place values of the individual signals? Yes. From left to right, they're 4, 2, and 1. And then this one will be 4, 2, and 1. And if there's a carry coming in on the right-hand side, it'll have a place value 1. You know, when you're doing an adding up calculation, you often have a carry in from the column before. Same deal. In general, we consider adding up 2 numbers and a possible carry. If you don't want the carry, you just send a 0 in, and everything works fine. Okay. So, how to proceed? Well, we've got 3 1s, 2 2s, and 2 4s. We could choose any adding at all. We could start with the 4s if we wanted to. It would just get more complicated, but we would get the right answer. It's generally a good idea, but not vital, to start with the lowest place value. So let's do the 3 1s. This diagram will get messy, I'm afraid. Add them together with a full adder. What comes out in terms of place values? A 2 on the left and a 1 on the right. So now you can see how many signals at place value 1 have we got left? 1. We've just got the 1. That means we found the 1s of the answer, but we've sent an extra signal of place value 2 to the left. That's the carry from adding up the 1s. And it has place value 2, and it needs to be added in with the next column, just like when you're doing an addition calculation. So our next move, I'll change color for it, is to, well, I'll change the color of pen. I'm not very good at changing color. Although I do sometimes go red. So we're going to add up the 3 signals at place value 2 with another full adder. What are the place values that are going to come out? 4 here, 2 here. And now, we've only got 1 signal left of place value 2. So that means, I should keep my blue pen for that. We figured out the 2s of the answer. So we're nearly there. All we have left are 3 signals at place value 4. And we can add them with another full adder. That's just the reminder to shut up. Right, so we have another full adder here, and we wire it up to. And what place values will come out? 4 on the right, 8 on the left. And now we have only 1 signal left at place value 4, and 1 signal left at place value 8. What would happen if we sent all 1 values into these inputs? What numbers would we be adding in decimal? 7, 7, and 1. So what would that bring us to? 15, otherwise known as 1, 1, 1, 1. So if we send in the largest possible inputs here, we get the largest possible output. This circuit is exactly built to fit. And you can see that it is constructed just by using a full adder to do exactly 1 column's worth of adding up. So if you've got 2 inputs and a carry coming from the previous column, a full adder gives you exactly the right circuitry to produce 1 bit of output and send a carry to the next column. So you can keep this going sustainably for as many bits as you want. This circuit is called a ripple carry adder. And this one is for 3 bits. But do you see how you would make a ripple carry adder for more bits? You take the next bunch of inputs and the carry from the one before. So here we would send the 8s instead of to the output into the next adder if we wanted to add an 8s column. So you can build adding circuits that work for numbers as large as you like just by adding a sequence of ripple carrying full adders, carrying down to the left. Now, one of the things, here's a warning, that happens in arithmetic circuits is that people think what they ought to do is memorize some diagrams. And 2 things go wrong when you do that. Thing 1 that goes wrong is that I ask you to solve an adding problem for which you have not memorized the correct diagram. And I will do that. That means you just need to know how adding works, not a bunch of diagrams. And secondly, one thing that I often see is when I ask for a problem where you do know the diagram, but your brain plays a little trick on you, and you write down the mirror image of the diagram, and then you will get not merely no marks, but also some mockery. Sometimes I see people try to draw me adding circuits where the carrying goes from the right to the left, because they've remembered that something like that has to be in the picture, but they don't know what it means. They are drawing a picture from memory, not from understanding. And what I'd like you to make sure that you do is understand why this picture is the way it is and why this is actually adding up. Why carrying goes from lower place values to higher ones. Okay, well that's what I planned to do for today. I didn't even fit it in the time, which is nice. So can I have your 1-minute papers on the way out? Your tutorial problems for this topic I put online about an hour ago. So if you want to get cracking on those, great. Remember, tutorial problems, your mark out of 5 doesn't matter. Having a go is what matters. And you have tutors to ask about them. So I've got spare 1-minute papers if anybody still hasn't got one.